I thought I would make this video to not only calculate multinomial probabilities, but to hopefully shed some light on why the PMF is what it is. So let's suppose that we have this magic machine and it spits out marbles according to the probability distribution that we see here. So we're going to get this machine to give us 8 marbles. And then out of those 8 marbles, what is the probability that we get 4 red, 2 green, and 2 black marbles? So let's first just put down one possibility. Maybe we get a red first, and then followed by a green. And let's see, we need to do maybe a black one. And then maybe we get a green one again. And then maybe a red one. And then another red one. And then a black one. And then another red one. Now let's see, did I do that right? There's 4 reds, 2 greens, and 2 blacks. Okay, that's correct. So this is one possibility. So then we need to think about, first of all, what's the probability that we got this exact occurrence? And then how many other ways could we get 4 reds, 2 greens, and 2 blacks? So let's see, let's think about it. Well, the probability that we could get a red on the first time the machine gives us a marble, that's 3/10. And then followed by a green, which would be 1/5. And so you get the idea. I'm just going to fill these in. Let's see, 3/10 there. And each one of these are independent, right? What the machine gave us last time has no bearing on what it's going to give us this time. So these are all independent trials. And so the probability that we would have gotten this exact outcome is, 3/10 to the 4th power times 1/5 to the 2nd power, and then times 1/2. Times 1/2 to the 2nd power. So this is the probability that this particular outcome would be reached, that we'd get this particular outcome. So now we need to understand where that multiplier comes in. So how many different ways could we reorder these things? That's the first question we need to answer. And to point out something here, now we don't care about order, but to illuminate that, I'm going to number the reds. I'm going to call this R1, R1, R2, R3, and R4. And then similarly G1 and G2, and then B1 and B2. This is exactly the same as if this were R2 and this were R1. Right? To us, we don't care if we call this one R2 and this one R1. It's still the same. That outcome is still the same. I'm going to put it back the way it was. So if we count up the permutations, because that's going to be sort of the next step, is how many different ways can we permute what we did get? And of course the answer is 8 factorial. If we took this one outcome and permuted it in every way possible, there would be 8 factorial of those permutations. But then we've got to account for the overlap, because remember before I switched R1 and R2 But there was still a red one here and a red one here, right? The slots where the reds were still there. It's just that I took this red here and put it there, and this red here and put it there. That's all I did. But that's still the same outcome as what we had to begin with. So we don't want to count that. We don't want to overcount those. And the permutations, this number does overcount. So to take care of not overcounting the reds, we divide by, well, how many different ways could I permute these reds? And the answer is 4 factorial. So we don't want to overcount the reds, and we don't want to overcount the greens, and we don't want to overcount the blacks. So that's why you end up dividing by that product of factorials. Okay, I hope that helped. It doesn't affect your ability to apply the PMF formula, but hopefully, if you're one of those people who likes to know why, hopefully that helps to answer the question for you.